one way to prove that a pair of formulas are equivalent is by using a truth table. Another way is to first lay down various general laws of equivalence and then use those laws to establish the equivalence in question. I'll demonstrate that second method here. So, one very simple law of equivalence is the law of double negation. It says that for any with alpha, alpha and not alpha are equivalent. So according to that law, P and not P are equivalent. But that's just one instance of the law. It also says that not P and Q is equivalent to P and Q. That not R or S is equivalent to not R or S, and so on. There are also what are known as De Morgan's laws. The first of these says that for any withs alpha and beta, not alpha and beta is equivalent to not alpha or not beta. In other words, denying a conjunction is the same as asserting that at least one of the conjuncts is false. The second of these says that for any withs alpha and beta, not alpha or beta is equivalent to not alpha and not beta. In other words, denying a disjunction is the same as asserting that both of the disjuncts are false. We can use these general laws to prove that a specific pair of formulas are equivalent. For example, we can use these laws to show that not P or not Q is equivalent to P and Q. To start the proof, I'll write down the formula not P or not Q. Now, one of De Morgan's laws tells me that negating a disjunction is the same as negating both disjuncts and conjoining them. So that law tells me that not P or not Q is equivalent to the conjunction of not P, the negation of the first disjunct, and not Q, the negation of the second disjunct. So as the next line in my proof, I'm going to write down not P and not Q. And I'll put this equivalence symbol in between the first and second lines to indicate that by writing this formula down next, I'm saying that it's equivalent to the formula immediately above it. And I'll cite De Morgan's laws here at the end of this second line to indicate that it's one of De Morgan's laws that justifies me in saying that this formula I've written down on the second line is equivalent to the formula on the first line. Now, the law of double negation tells us that not P is equivalent to P. So I'm going to write P and not Q down as the third line in my proof, asserting that it's equivalent to the formula immediately above on the second line. But what exactly justifies me in saying that this third formula is equivalent to the second one? This is a subtle point, but note that the equivalence of line 3 with line 2 is not one of the equivalences asserted by the law of double negation. What the law of double negation tells me about P and not Q is that it's equivalent to not P and not Q. That law by itself doesn't tell me that not P and not Q is equivalent to P and not Q. To conclude that those formulas are equivalent, I need to assume not only that not P is equivalent to P, which is something that the law of double negation tells me, but also that because not P and P are equivalent, we can swap one for the other inside of a formula, and the new formula after we've performed the swap will be equivalent to the formula we had before. So we'll refer to that extra assumption as the law of substitution. So the law of substitution says that replacing a subformula of a with by an equivalent expression, in this case we replaced not P with P, results in a new with equivalent to the original one. So our justification for saying that line 3 is equivalent to line 2 has to appeal to both the law of double negation, since that's what tells us that not P is equivalent to P, and the law of substitution, since that is what tells us that if we replace a subformula in a with something equivalent, the new with is equivalent to the original one. Next, as the fourth line in the proof, I'm going to write down P and Q, claiming that it is equivalent to P and not Q. Once again, as justification for that claim, I'm going to cite both the law of double negation and the law of substitution. Our reasoning shows that not P or not Q is equivalent to not P and not Q, which is equivalent to P and not Q, which in turn is equivalent to P and Q. So it shows that not P or not Q is ultimately equivalent to P and Q by establishing a chain of equivalences, taking us from the former to the latter. Let me make 4 further comments here. First, at each step of the proof, we either apply a single law of equivalence, which is what we do in going from line 1 to line 2, or if we're taking out a subformula and replacing it with something equivalent, as we do in going from line 2 to line 3 and line 3 to line 4, we apply a single law of equivalence along with the law of substitution. It's only when we perform that maneuver that we appeal to 2 laws at once, namely the law that shows the subformula and the thing replacing it to be equivalent, and the law of substitution itself. Second, we only ever perform one substitution at a time. So rather than jumping straight from not P and not Q to P and Q, we first replace not P with P and then replace not Q with Q. It wouldn't be terrible to allow multiple substitutions at once, especially if, like in this case, it's the very same law justifying each substitution. But if it's different laws justifying the different substitutions, it gets harder for the reader to follow what's going on. And the whole point of a proof like this is to take a pair of formulas that are perhaps not obviously equivalent at first blush and make it obvious to the reader that they are indeed equivalent by patiently showing why. We don't want to undermine that by trying to do too much in a single step. Third, from this point forward, we'll refrain from writing the equivalent symbol in between each pair of lines. We'll just take it to be understood that every time we write down a new formula, we're asserting that the new formula is equivalent to the formula on the immediately preceding line. But of course, we'll keep the note at the end of each new line that gives the justification for saying that the new line is equivalent to the one immediately before that. Finally, I'll point out that we could have proved the same result in a different way. Rather than starting from not P or not Q and then establishing a chain of equivalences taking us from there to P and Q, we could have gone the other way around. To do the proof that way, we start with P and Q and then write down not P and Q as line 2, citing the law of double negation. Next, notice that not P and Q is a subformula of not P and Q. And one of De Morgan's laws tells us that not P and Q is equivalent to not P or not Q. So by the law of substitution, we can replace not P and Q in the original formula with not P or not Q, and the resulting formula will be equivalent to the original. The formula that results when we perform that swap is not P or not Q. So as the third line of the proof, we can write down not P or not Q and appeal to De Morgan's laws plus the law of substitution as the justification for saying that that formula is equivalent to the formula given at line 2. We've now established the same result as before, namely that P and Q is equivalent to not P or not Q, but this time by starting from P and Q and ending at not P or not Q. And this way of doing things actually resulted in a slightly shorter proof. So if you're trying to prove that a pair of formulas are equivalent using general laws of equivalence as we did here, and one route to your goal doesn't seem to be working, it's good to keep in mind that you can also try the alternative. That is, rather than starting from the first formula and via chain of equivalences arriving at the second, you can also try starting with the second and ending at the first.